that's how it runs. So up here we have some imports to randomize to create my cost grid, numpy to handle the arrays, and some of the math, and the math to truncate some of the decimal time sleep to make the sleep timer, and then also heap q, which is the queue I'm using. So we have the seed here, which is 15. It's just for the costs. Then we have the lowest cost, which is equal 1. Then we have grid, which is 2020. Then we have start and goal. What's interesting about numpy is it has the y value first and then the x value. And then we have the map grid and the path grid. They are the exact same. Inside the map grid we have some different values. 9 is walls, and the others are just for an interesting addition. So then we have path grid start, and then we have path grid goal. That's just to say what is the start and what is the goal values. Then we have create cost grid, so we have cost grid and the heuristic grid. Cost grid gets the randomness, and then we have the heuristic grid, which gets the absolute y value minus the goal value y value, and then the absolute of the x value minus the goal x value times lowest cost, which is 1. And then it returns the cost grid and h grid. Then we have the print grid, which is just printing out the nice little visualization, and then it also has the cost grid and the h grid. This is where the trunk comes in, because cost grid and h grid had some annoying decimals. Okay, and then we have the AStar, so the fancy stuff. So first I make a queue, which is a list, and then I heapify this queue to and then we have the heap push, which adds an element to the heap. So what's fancy about heap is that for every addition or removal, it sorts the list according to a priority. And in this case, as you can see in heap push, first it gets the queue, which is the heap, and then it gets a tuple of 0, which is the priority, and then start with, which is my coordinate tuple, so any data value. Then we have a came from list and a cost so far list. So while the length of the queue is not equal to 0, then we have current equals to heap pop, so it means to take an element out of the queue. And since it's always sorted, it should be the lowest priority. And then because of the way the tuples work, I actually had to do some interesting stuff, because I had to actually take the cost out of the queue. So I had to take the tuple out of the tuple, and then if cost is equal to goal, we break, and then we have the map grid y x minus 1 equals not equal 9, which is the wall, and then path grid is not equal to 7, which is if we have burned it. So there's no reason to check it if that's the thing. Then we have new cost equals cost so far to the coordinates plus cost grid y x minus 1 plus map grid. So as I said earlier, map grid has some fanciness with the numbers that is not 9. So I just add those to the cost. And then we have the cost grid as mentioned, which is the randomness. Then we have path grid equals 10. That means it has been checked, is the C's. And then if yx minus 1 is not in cost so far, means it hasn't been added yet, or if the new cost is below cost so far, then this happens, which is cost so far equals new cost, and priority equals new cost plus h grid, and here's the heuristics. Because they are not part of the actual cost, they need to be added for the priority only. And then we have heap queue heap push, which has the element, and then we have came from equals chords. The other 3 blocks are the exact same thing. It's just the x values plus instead, and then the y value minus, and then y value plus. So nothing really fancy there. And then path grid equals 7, which means it has been burned. And then we print the grid, and then we sleep for 0.1 seconds. And down here we have the stuff that's actually happening. So cost grid, h grid is created, print the grid, then the whole AStar thing happens, and then we print the grid at the end because we break the loop. So what should be added to this is the pathing, but I simply did not find the time to do the pathing.